This lesson is thin-walled pressure vessels. Up until this point in the class, we've been, talking about stress by itself, and then talking about strain by itself, and then talking about combining stress and strain. And then, like I mentioned a week or so ago, we're now moving into the time of the class where we're talking about applications and using stress and strain in various situations. And what we've just been doing for the last several days is axial loading, and that's one of our applications, just an object that's loaded axially. And this is our next application, is thin-walled pressure vessels. And today we're going to talk about what makes a pressure vessel thin-walled, and we'll talk about axial stress and hoop stress, and then do an example problem. The first thing that I'll talk about a little bit here is just to say what is a pressure vessel. So this LNG tanker that you see here, these spheres that are in here, these are pressure vessels, and inside there we've got pressurized gas, and it's stored in there under some amount of pressure that tries to push the outsides out, and basically that makes our pressure vessel. And that's a pressure vessel. An airplane like this is a pressure vessel. The reason that I have this particular picture is that this wind tunnel that this model is in, the National Transonic Facility, is actually a very unique wind tunnel. It is a pressurized wind tunnel. So you see this loop down here in the picture. The entire wind tunnel itself, the tunnel itself, is a high pressure vessel, because what they try to do in this wind tunnel is really increase the temperature and really increase the pressure and really drop the temperature, because by doing so you can greatly increase your Reynolds number. And if you remember from fluids, one of the things that you want to match if you're modeling something is the Reynolds number. And so this particular wind tunnel can match basically full-scale flight Reynolds numbers in the wind tunnel. Pretty cool. It's a ridiculously cool facility. This Dr. Pepper can is also a pressure vessel. The Orion crew capsule is also a pressure vessel. So let's now talk about what makes a thin-walled pressure vessel. What does thin-walled mean? And basically what it means is that the distribution of normal stress in the surface of the vessel is uniform throughout the thickness. So what does that mean? Let's draw a picture here. If I have a sphere like this that has some sort of a pressure in it, a pressure that's pushing on all the walls. Let's say that we cut this thing open so that I've got I can look at the thickness of this thing. Like this is the thickness, the face that I just cut open, and basically along that thickness or through that thickness, the stress is uniform. So the stress throughout that thickness there is uniform. The stress basically that's holding the sphere together. And basically we're going to say that. Well, I shouldn't say we're going to say. I mean, this is true, as you can see down here in the note. The stress is normal throughout the thickness if the ratio of the wall thickness to the inner radius of the vessel is less than about 10%. So you can see that down here. So let's take a look at how we're going to actually analyze this thing. First, we'll consider a sphere. So just like I drew a minute ago, we have some sort of a sphere like this. The internal pressure inside that sphere is P, and the thickness of the shell is T. And what we're going to do is draw, again, a sphere that's been opened up a little bit. Actually, let me change the look of that thing a little bit. I want to turn it a little bit more. So I've got like this. So there's my sphere, and let's draw a set of axes here. So I've got X and Y and Z like this. And what we're going to say is that acting, I'll change the colors here a little bit just to make things clear. Acting kind of this way into that sphere is I'll say capital P, and that's going to be the force exerted by the internal pressure. And that force is going to be pi r squared times that internal pressure, that little p. So the radius of this thing, the internal radius of this thing is r, little r. All right. And now, in case I didn't make it clear enough, which I didn't say this yet, but what we're drawing here is going to be a free body diagram of this thing, chopped in half like this. All right. So I'll change the color again, and I'll change this to blue, and all around the outside of this thing, we're going to have stress, pulling in the opposite direction, of that pressure. Get rid of this last one here. All right, so I've got a normal stress acting all the way around there, and I'll call R the force exerted by that axial stress. That's a normal stress that we call the axial stress. All right, and that is going to be given by 2 pi r times T times sigma A. All right, and sigma A is my axial stress. All right, that's the stress that's acting through the thickness of that pressure vessel. All right, and 2 pi RT, this is the area over which that thing acts. All right, and it's basically the area where I have all of these little blue arrows. All right, so now if I go back over here and say let's sum our forces in the x direction, we're going to get R is acting in the plus x direction. I don't know why I keep getting that funny line on there. R is acting in the plus x direction. We've got P acting in the minus x direction. That equals 0. All right? So that means that R equals P. And if that's the case, then that means that 2 pi R T times sigma A is equal to pi R squared P, or the internal pressure. All right? If I then solve for sigma A, I get this. Right? So my axial stress, basically the normal stress that's acting inside that thickness of the sphere, is the internal pressure times the radius divided by 2 times the thickness. And this basically goes for any direction you choose on the surface of the sphere. So if I draw a sphere like this, I could draw a little stress element. I'm going to have sigma A acting in every direction. Because this little chopping thing I did to cut the sphere in half, I can do that anywhere, right? I can do that in any direction I want to. So it doesn't matter where on the sphere I draw my little stress element. I'm always going to have sigma A acting like that. All right. So let's consider another case. Another case is a cylinder. So instead of having a spherical pressure vessel, we'll have a pressure vessel that's more like this. All right. And in this case, I've got a stress element acting like this. All right, and I'm going to have a different stress in each of these directions. So the direction like this I'm going to call the axial stress, sigma A. And the stress in this direction is the hoop stress, sigma H. All right. So the first thing we're going to do is work on finding an expression for the axial stress. Right. So in that case, I can draw. I can slice this cylinder open again so that I can see down the. I should say so I can see the thickness of the thing exposed over here. And again, let's draw axes like this. So this is the x direction, y direction, z direction. All right, and in the same way that we just did for the other one, I'll draw pressure acting this way. All right, and I've got sigma A acting this way, all the way around the outside here. Oops. So along the outside here, I've got stress pulling back the other way. So the balance is between this stress on the outside, sigma A, or I should say the force that's exerting, and the pressure that's pushing in the opposite direction. I should say the pressure force right here. So my pressure force, big P, is going to be pi r squared times the internal pressure. That's the same that we had before, and I should say that's the same as we had for the sphere, and the resultant of all that normal stress, that axial stress, sigma A, is going to be 2 pi r t times sigma A. And that also is quite a bit like what we just did for the sphere. So if we do our sum of the forces in the x direction, that's going to look like P minus R. Again, we have P equals R. And again, we have pi r squared times pressure equals 2 pi r t sigma A. So that's sigma A is equal to the pressure times the radius over 2 times t. All right, and for that case, the axial stress, that's the same as the sphere. Now, we also have that hoop stress that we want to figure out, so let's work on the hoop stress next. So for the hoop stress, we're gonna draw a slightly different version of that cylinder here, but I'm going to cut it the other direction. So you'll see what I'm doing when I draw the rest of this thing in. Like that. So now I've sliced it kind of the long way, and I've got, again, axes here, x, y, and z. All right, I just realized I changed my colors. Sorry about changing the colors there. Let me go back to green for the pressure. So I've got pressure that's going to be acting this way, and I'll say the pressure force, big P. Pressure force. Good grief, that doesn't look so good. And then I've got stress that's acting in this opposite direction, this way. And that's sigma H, the hoop stress. All right, and if I sum my forces in that z direction there, I'm going to get the force from that hoop stress minus the force from the pressure, and that hoop stress now, if this length right here is L, then the area over which that hoop stress is acting, you know, this area here, whoops, and this area here, that's the area we're concerned about there. That's going to be L times T. T is the thickness, times 2. So 2 times L times T times sigma H. And the pressure is acting over L times 2R times the pressure. That's going to equal 0. Right, so this is R, this is my P, this right here is my area over which my hoop stress is acting, this right here is the area over which that pressure is acting. And if I solve for my hoop stress, then I'm going to get the pressure times the radius divided by the thickness. All right, so you can see that the hoop stress here is double what we just got for the axial stress. All right, that's noted down here. And if you have additional stresses, like from an axial load or something else, you can just add them. You can just add them to sigma A and sigma H because of superposition, which we talked about a couple times ago. All right, so the next thing we're going to do is an example problem with this cylinder. But in order to manage the size of these videos, I'm going to stop here. So part 2 we'll pick up right here and look at this example problem.